Good afternoon, everyone. Today, the Apton seminar has the great pleasure to welcome Professor Silvana Mattedi. Professor Mattedi is a full professor in the Department of Chemical Engineering at the Federal University of Bahia. She earned her doctorate in chemical engineering from the Federal University of Rio de Janeiro and completed three postdoctoral positions at different institutions: the Federal University of São Carlos in Brazil, the University of Santiago de Compostela in Spain, and at the Monash University in Australia. Professor Mattedi research focuses on applied thermodynamics with emphasis on equation of state, green technologies in waste treatment, solvents with low environmental impact, and characterization of materials. Thank you very much, Professor Mattedi, for sharing your knowledge and experience with us, and please feel free to start your talk.
So, although I do have a thermodynamics background, I will talk a little bit more on materials, on treating materials with ionic liquids, and the separation of cellulose nanocrystal from natural fiber with ionic liquids. So, why it's not working? Okay. As told, my background, I am a chemical engineer. I did my master and my doctor degree at Rio. Part of it I was working in UFBA. And then from there I did a postdoc at UFSCar working with quantum mechanics. And then I went to Spain in 2009 and I began to work mainly with ionic liquids with different applications, different properties. And in 2009, I went to Melbourne, Australia. Salvador is 1,631 kilometers from Rio, so long away, northeast of Brazil. It's the first capital of Brazil, founded in 1549. It's known by music, named the City of Music by UNESCO, and also by carnival party and African influence. The population is for almost 4 million, and the UFBA, the university where I work, hosts the first civil undergraduate course in Brazil. The university is from 1948. The medical school, that's the first undergraduate course, was founded in 1808 by President John, after John VI, of King of Portugal, Brazil, and Algarves. The university has a lot of courses and is 26 in the Latin American, one of the Latin American rankings, and in the other 72. I work in the Polytechnic School. We have 11 undergraduate courses, 6 graduate courses, master and doctors. And in chemical engineering, we have around 500 students, 8 master students, and 8 doctor students. So now I will do a little bit introduction why we are interested in that. We are interested in biorefinery. Biorefinery is an important concept that you could obtain different compounds from biomass, from vitamins, polyphenol, alkaloids, ligno-cellulose materials. And part of the processed biomass are residues. A great amount of residues is generated and processed in biomass, and these residues are full of very fine chemicals that have a lot of applications. So it's very important for a country with a large biodiversity as Brazil to have a look on biorefinery. Here I will more work on ligno-cellulose materials, but as concept is important, and it is important to achieve Some of the goals that from 2030 United Nations Sustainable Goals, mainly the 1, 6, 7, 8, 11, 13, 14, and 15. All these goals are connected with a rational use of biomass from with in different works. So another question is polymers. We have polymer is a very important material. You have a lot of uses of polymers, and they are interesting. However, normally they are non-biodegradable when they have a petroleum source. And we have a lot of incorrect disposal, long life cycle in the environment, causing a lot of environmental problems. One solution for this is to go for biodegradable polymers. There are synthetic biodegradable polymers like Ecovio. Ecovio is from BASF. It's a mixture of PBAT and PLA, that is polybutylene adipate, chlorothalate, and polylactic acid. However, although they are easy processability and biodegradable, they have low mechanical properties. So one idea is to reinforce it, and the idea is to reinforce with cellulose nanocrystals. When you talk about ligno-cellulose biomass, you can obtain from different source of biomass. Here we worked with bromeliad and part palm fruit, part of rambutan, and different materials. But it's possible with sugar cane, eucalyptus, cotton, etc. You have different source of materials. And if you look for the structure, you have in the secondary wall, normally cellulose, lignin, and cellulose, and the cellulose have nanocrystals of cellulose. That's nanocrystal of cellulose that we are interested also in lignin, but we do not use it a lot, work on lignin, but it's important as well. We worked here, we was not focused on lignin extraction for this specific work. We are not focused. We basically use the traditional work, blanking and soda treatment. The liquor is filtered, precipitated with sulfuric acid, and you obtain lignin through centrifugation. But from we did some works on lignin extraction before. First with Unicamp, they were interested in second generation ethanol. So they used different protic ionic liquids, including sulfuric and acetic ionic liquids. And for second generation ethanol, the best ionic liquids was, the best ionic liquid was 2-hydroxyethylamine acetate. However, in a later work, was not in this work, they saw that the lactate preserved better the lignin structure. So if you want to use the lignin, it's better to use lactate. Also, we work with the lignification of pineapple crown together with Professor Álvaro Lima in UNIT, Tiradentes University, and they are interested in a support for enzymatic immobilization. So they are interested in preserve the cellulose content. So in this case, this is bis 2-hydroxyethylammonium. So we have 2-ethylammonium. Acetate also has a better performance. There is a work from Unicamp with João Coutinho's group, Path from Aveiro. and they studied craft lignin, and they conclude that the anion influences more than the cation, the anion influences more than the cation. If you have a larger chain in the anion, higher is the solubility. If you have a smaller cation with a lower hydrox groups, also favor the solubility of lignin. But we are interested in cellulose. We first tested the acetate with 2-hydroxy-2-ammonium. It's ethanol ammonium, if you are not supposed to eat. They suspended the alpha cellulose. They not dissolve the cellulose. Alpha cellulose is not the best, it's not a raw material. What we did was sigma Aldrich alpha cellulose, and what they do is cleaning fibers. So they are used as alternative. Oh, I did not put the reference here, sorry. Used to mercerization, acetylization. We also used this kind of ionic liquids, and we tested different ones for preparing fibers to adsorption. Sorry for that, I don't put the reference here. But in this work, we are more interested in obtaining the nanofibrils of cellulose. Normally, the work is done with sulfuric acid. So what he used was sulfuric hydrogen sulfate anion with two different cations. We use 2-hydroxy-2-ammonium, and also we use aprotic ionic liquids, that is the 1-methyl-3-butyl imidazolium that has this structure. Here are the sigma profile of these structures. They were generated using JOTA-Cosmo, and you can see that the butyl ammonium has a larger dispersed area, lower positive area, and the area for 2-hydroxy-2-ammonium is much more positive, and part of it has a negative structure. And also, I don't put the acetate sigma profile, but the hydrogen sulfate is much more negative, induces more a positive response because it has sulfuric with oxygen, and also other 4 oxygen, and it's more protic compound. So just to see the pH here, I think it's around 6 or 7, and if you use the 2-hydroxy-2-ammonium, but if you use hydrogen sulfate, we are talking about 1 to 3. So what nanocrystals of cellulose is? So cellulose nanocrystals is the fiber. Normally, you have a crystalline domains that is present when you have at least 1 nanometer sized. So if you have a 1 nanometer sized in any dimension, it's called nanocrystals. And you can see from the tree to the wood to the tissue, microfibers, nanofibers, nanocrystals. You are, the structure is maintained even in a nanoscale. So you have a crystalline domains and amorphous domain. Here are some samples from sisal. It's agave. I don't know if the translation, but it's agave, sisalan, the plant, or cotton. They have different cellulose nanocrystal that can be extracted. Normal, the extract is done with sulfuric acid. So the most conventional way is sulfuric acid. However, there are some ionic liquids. Nanocrystal obtained from cellulose microcrystalline. We obtained nanocrystal in a previous work with 2-hydroxyethylamine, and also we use the imidazolium. So we use aprotic and the aprotic ionic liquids. You can say they are different nature, but what we have in the literature was the bemene hydrogen sulfate. Maybe I can use the H-mean for compare, but we are more, we use more ethyl ammonios and ammonios in general in our lab. So we choose this one. They have less severe continent conditions with sulfuric acid, and most important, we proved that the ionic liquid could be reused, protic and aprotic. We can process and after reuse the liquor more than one time. So we have different applications for this nanocellulose, different applications from textiles to films, personal care products, oil, coatings, adhesives, paper, healthcare for bands, aerospatial, security inks, automotive, textile. So different applications. And here, what is the objective of I put this work? First, we use different source of cellulose. We obtained the nanocrystals of cellulose with sulfuric acid and with the ionic liquids. We prepared the polymer for mixing lignin and Ecovil, that is PBAT with PLA, for a polymer preparation to extrude it better. And also for casting, we prepared the nanopaper. So we have nanocomposite and nanopaper materials. We use different vegetal fibers. We use bromelia, Neoglaziova variegata, that is from Brazilian Northeast, has a high cellulose content from the leaves. Also, we use rambutan that is present in Northeast as well. The fiber is in the peel. We use the peel, not the fruit, for obtaining the fiber. And we also obtained, but with traditional manner, so we're not showed here, lignin from the peel. We also use recycled cardboard that 100% of the cardboard used is recyclable, and 100% of it is from renewable source. However, only 65% is recycled. We also use algae, uva latuga, that's this one here. This is a present in Brazil, present in Northeast, and also sometimes it is a problem because it can proliferate very quickly depending on the conditions of the system. So it's interesting to use this material. It has a very low lignin content. Okay, I don't have much work on this. I do have, but it would be very long. So we focus on the first two, but we also did with these different materials. We prepared the nanocrystals with sulfuric acid. That's basically hydrolysis, centrifugation, and then dialysis. This material for the composites we named NCC. Or we synthesize the ionic liquids. We normally synthesize them in the lab. For the bimine, we bought it from Sigma Aldrich, but the ammonium, the protic-ionic liquids normally do at the lab. The difference here is that from the traditional synthesis is that we need really to use a very low temperature because and very careful dripping of the acid on the amine. It's we use 8 degrees Celsius. Oh, sorry, 2 degrees Celsius. It's very low temperature because if you put directly the amine in the acid, it's a very quick reaction and it can explode. We have seen in the literature what they do normally is to put a lot of water. As we don't need so much water, we prefer to do it concentrated in low temperature. So the NMR was used to characterize purity. We have a purity higher than 95 and no content of water. It's a high content of water if you compare with other things, but low content for these ionic liquids. If you put in molar basis, a lot of water. But then we preparate the nanocrystals with the ionic liquids a little bit higher the temperature. So we have two kinds of nano whiskers. And then we prepare the nanocomposites. Here we use the palm fruit as work from Bahia. It's very interesting to have palm fruit. For people who are not from Brazil, our food, we eat palm fruit. We eat fish and things like that cooked in palm fruit virgin oil. But so we have a lot of residues of palm fruit here, and we extract lignin and mix it with EcoView. EcoView needed a little more PABT, so we use 50-50 and a little percentage of lignin. Of course, we did experimental. How can I say that? We did experimental analysis of the conditions, statistical experimental analysis of the conditions. So we have different ionic liquids that output of them. We tested different temperature for extrusion as well, and you have different nanocomposites. So for nanopapers, we use here are more the components from rambutan. We use for the sulfuric, the aprotic ionic liquids does not work very well. Sorry, for the protic ionic liquid does not work very well. But for the aprotic ionic liquids, we obtain a cellulose that is spherical because that we put this name. And this is traditional obtained that is cylinder form nanocellulose that comes from the sulfuric acid. After obtaining it, so the same process, dissolution, and after dialysis, centrifugation, and after dialysis, this is the Biorefinery test that we needed to know if a suspension is formed. So, and then we used a casting procedure to obtain the nanopaper directly. So it's pure cellulose from this. Just evaporate the solvent, and then we have the nanopaper. We characterize all of them with microscopy, atomic force microscopy, thermogravimetry, diffractometry of X-ray, infrared Fourier transform, and also with the solution, the analysis of the solution with the zeta potential. The thermogravimetric materials show that they have similar similar behavior, and the protic one has a lower degradation temperature, and the from sulfuric acid you have a higher degradation temperature. If you go for the crystallinity index, that one thing that we are very interested as we want to reinforce materials, the crystallinity index is much higher when you use sulfuric acid. So we have a lower removal of the amorphous regions. And for the protic ionic liquids is even better than the aprotic one. Here I am using protic ionic liquid for the ammonium and aprotic for the imidazole. So all of them have the cellulose typical bonds and sulfuric bonds. The sulfuric bond is much more present in the ionic liquids treated material, and also a higher band of OH, hydroxyl bonds, that as here you use hydroxyl ionic liquid is much higher than you have for sulfuric acid or for the bimine material. We did the transmission microscopy, and what is that we have different materials. For the nanocellulose, for sulfuric acid, you have a crystal needle shape, and also needle shape for imidazolium, and a spherical shape for protic ionic liquids. The same we can observe with the atomic force microscopy. And for the zeta potential, that is very important to see if the suspension is considered stable. So the suspension is not stable, so you can separate the microfibrils and the nanofibrils. And it is the protic ionic liquids that achieves more stability, although they are spheric. So the presence of sulfate, hydrogen sulfate, that came from hydrolysis, act as electrostatic repulsive force. And so they have a direct influence on the suspension stability. And also, they do have mechanical properties, and the mechanical properties do not vary so much. And for elongation, that's very important for processability of the material, is much better with the imidazolium. But for the other, it's a little bit better. But for stress at break does not change very much, and also the elasticus model. Thus, the variation is not that important. And here are the transmission electron microscopy of the material. Not only the first part was only using the fibers, and here is the nanocomposites. So here we have also the polymers. So for the protic ionic liquids and for the aprotic ionic liquids, although here the fibers were cylinders, when it goes in the material, it has a spherical shape, and you can see some part of the agglomerations forming in the material. The same thing we can see for the both ionic liquids, but it does not occur when you use the sulfuric acid. But the thing is, both of them, as they have different, they have the same properties, mechanical properties. Both of the three materials could be used as nanocomposite, for example, for tree seedling in reforestation, because what we want is that after a while, the material disappears into the land, does not continue to be there. So they are biodegradable, and our stats preliminary that they degraded in 10 months. So we can use this material as to contain the seedlings for trees. We used, we now are this work, what we have the conclusions for this part. We have, we tested the three methodologies, and we obtained cellulose nanoparticles with all of them. The sample with project ionic liquid presented spherical shape. The cellulose present higher crystallinity and higher thermal stability, but the thermal stability of the three materials could be used in extrusion, because we have to test it, because after the material is extruded. And although the nanoparticles had different shapes, they had similar mechanical properties. So ionic liquids are able for separate crystalline nanocellulose from the amorpho phase from biomass, and nanocomposite with sulfuric acid, with the approach ionic liquid is show the higher deformation, so the elongation is better. So it's important property if you want to do films. Ionic liquid can be used to obtain cellulose nanoparticles, and they could be recycled. We tested the recyclability, so this is very interesting, because one main problem with the sulfuric acid that you cannot recycle it. Also, through the microscopy, it was observed the presence of nanoparticles in the polymer matrix, and they agglomerate in the polymeric matrix. So now I will go back to the nano paper. Here I will ask a little bit, I will translate for you, because I could not translate all the materials, but we have here the raw peel. The first photo here is the raw peel. After we just clean it with water. After we extract with ethanol to most of the extractives of the fiber, and after we pulped the fiber and blanked the fiber. This liquor that was used for producing lignin, and we are able to produce lignin, is not here because it was not the focus, from the liquor obtained here from rambutan. And you can see the characteristic bands of each compounds, of the characteristic compounds of cellulose, and you can see that the treatment leads to a higher crystallinity. Higher this angle, higher the crystallinity. So if the peel after just cleaning has a lower angle, a lower peak, lower intensity of this peak, and after extraction, it's a bit more, after pulpation, a bit more, and after blanking, a higher pulpation. What is happening in the fiber, what is really occurring, that you are cleaning the fiber. So the pre-treatment is cleaning the fiber. Here has no ionic liquids, but it's interesting to know what really occurs. And this is similar what we see in that work that I mentioned, that we use the ionic liquid to clean the acetate, to clean the fiber. We tested sulfuric acid also, but it was not efficient for us for what we want, that sulfuric acid, no, sulfur, hydrogen sulfate ionic liquids, the ammonium sulfate and different kinds of ammonium. But we are interested in produce a rugose superficie for adsorption. So it was not so good as acetate materials. However, here we are interested also in obtaining the cellulose nanocrystal, so sulfuric is more indicated. If you pick the nature of the material, so with the spherical shape paper we have here is the cellulose from rambutan, the cylindrical cellulose, and the spherical cellulose that here we obtained with sulfuric acid, and here with the ionic liquid, the aprotic ionic liquid. And you can see that they are similar. However, the spherical degrades a little bit before and has a lower crystallinity. So, and you can see that it's more, the polymorph of cellulose 1 is more present than the cellulose 2. There is no cellulose 2. So what you see when you recover the solution is that the same profile, FTR profile, is recovered. So we can reuse it a lot of times. And we produced papers with this material. What we are interested in here is transparent papers. So like we used to use it a lot, but it's not common nowadays. We use acetate film to present in the conference. But now we use more the computer, so it's not common anymore. But this transparent paper has also use for materials. So they have similar transparency. You can see here we printed with different colors, the name of the university. This is the paper, and it's a photo of the paper, and you can clearly see the transparency. So what we did is there is a printed paper, and they put the paper, it's not printed in the transparency, we printed and put the paper above it. So in the photo, you can clearly see what is written below it, that's what we want. So the spherical cellulose has a characteristic that is interesting. Although it has a lower capacity to redisperse in water because it has a higher hydrophobicity, they have similar transparent and a less packed layer structure for the nanopaper made of the spherical nanocellulose. So the distance between the layers here is 200 millimeters. So we draw the conclusions that the spherical nanocellulose is successful isolated from a soft cellulose source as rambutan peel. We could isolate also different materials from the other materials, but we would not put everything, so it would be too long. So we use the hydrolysis with the aprotic ionic liquid, and we can do it in a short time. So you can do it in more quickly. You can obtain the cellulose with the ionic liquid. The spherical has good stability in water. We have a slightly better thermal behavior than the commercial nanocrystals. That is interesting. The cellulose present is polymorph cellulose type 1, although we have a low crystallinity for the paper. Nano paper are probably less packed than the circular nanopaper, the cylindrical nanopaper that are done using sulfuric acid. And so this ionic liquid is an alternative medium to isolate spherical nanocellulose. So now I would like to acknowledge mainly to my students and to my colleague, Professor Nadia, that I was a co-supervisor. She is more on materials. I did more the ionic liquid to test and see what is working. And also they sponsor the labs, the sponsors, and also to the Atoms organized and to you to be here.